Hello YouTube viewers, this is Victor Echo 6 Whiskey Golf Mike here with you from the bustling metropolis of Hythe, Alberta, Canada. All 900 population of us. So it's kind of a miserable day outside. It's about 2 or 3 degrees above freezing, raining and blowing outside. So I'm going to spend a little bit of time in the hobby shack here. And I wanted to do an experiment. It's kind of been nagging at me a little bit. Curiosity, I suppose. But in addition, I've also received a few comments about the use of the Alligator test leads here. The Alligator clips are pretty crude when it comes to vector network analyzers as far as measuring the values of components. So anyways, this here is simple, it's quick, easy. You know, for a lot of ham radio operators and hobbyists, if you're measuring, you know, the nominal values of components like this, the frequencies that are used to do that are so low that this test apparatus here really it's good enough. And honestly, you know, in the past videos I've shown quite clearly that it actually does give the correct values. So I'm not worried about whether this works or not. It does. And but here's the thing. What's the difference between using this and using something like this, where a lot of people would that have complained about or scoffed at the use of Alligator leads? You know, they suggest that a proper a test fixture should be used. This is probably approaching something that's a little more accurate, perhaps, or a little more formal than Alligator clip leads. Probably not as accurate still as a proper, you know, dedicated test apparatus that is specifically built to minimize stray capacitances and inductances and to ensure that you get the highest accuracy possible. But again, coming back to, you know, measuring these values, does it really matter if your reading is 15.001 microhenries or 15.002 microhenries? Just the fact that you read 15 microhenries is sufficient to know that you've confirmed the value of this inductor for most of us. If you're going to start using this in a circuit that requires precision at higher frequencies, then the methods that I'm presenting here are probably not going to work for you, and you should probably go to greater lengths to try to characterize this component at the frequency that you're actually going to be using it at, so that you don't wind up with some unexpected behaviors. Anyhow, with that being said, what I'm going to do first is I'm going to do a full short open load and through calibration on the nanoVNA here, because what I'm going to do is measure this inductor using this test board kit here. I'm going to use the shunt configuration to start off with, and then what I'm going to do is adjust the component. I'm going to measure, actually here, I'm going to measure two things. I'm going to measure an inductor and a capacitor using the shunt method on this test board kit here. And then what I'm going to do is I'm going to place them into a resonant tank circuit, and then I'm going to take the through measurement, the S21 parameters off of this, and use that to verify that the values that I've read for these components are correct. I'll show you how that's going to happen here shortly. So let's get to it. All right, so we've got our cal standards laid out here, and we've got the short, the open, and 2 loads, and I'll show you in a second why I have 2 of these. But first off, before we begin calibrating, we have to decide what frequency range we're going to be using on the nanoVNA. So we should probably go in and set our stimulus, and I'm going to start it at 10 kilohertz, and I'm going to stop at 20 megahertz. And off the top of my head, usually for what I've been doing, I've learned that that's usually a good frequency range to calibrate for. So we're going to go ahead and begin the calibration now by resetting and hit the calibration. All right, now, so the open, we're going to connect a coupler here, and I'm going to use the open, has no pin in it. All right, there's open. And we're going to Here's the short. You'll notice when you're calibrating, when you watch it, the open should be somewhere on this side, the short should be all the way over here, and when we go to our 50 ohm load, it should wind up right in the center of the Smith chart here. It's kind of a little bit of a verification for you that everything is working, you don't have any issues with your cables, and that the connections are correct. So there's our short, and now we hook up the 50 ohm load, and you see that it does go to the center of the Smith chart. Now for isolation, we're going to hook up a 50 ohm load to the cable connected to port 2, and that's just to make sure we don't have any noise or anything getting in there while we're doing our isolation calibration. And then we go ahead and we connect the two together to do the through. And we're done. So I'm going to go ahead and save that, and we're ready to go. All right, so back to our nanoVNA test board kit, and we're going to go ahead and connect port 1 to the inside of this. And I'm just going to arrange these cables so that this will lay flat on the table here. All right, and the out goes to port 2 on the nanoVNA. All right, excellent. So now I'm going to connect the inductor here, poke it into these sockets here. Here we go. Excellent. Now we're going to start taking a look at what we got here. So we can see right off the bat, you can see the self-resonant point here of this apparatus with the inductor attached. All right, so back to measuring the component value. We definitely want to stay away from that self-resonant point. You're not going to get a very good reading there, like was demonstrated in previous videos. You can see I've got 126 microhenry reading here. So what I do is I actually go and look for the point at which this marker here is at the 12 o'clock position on the Smith chart. And you can see that we don't have very good resolution here. It's jumping back and forth between 82 degrees. We want it to be 90 degrees and 105 there. So what I'm going to do is readjust the stimulus frequency, and we're in around 600 kilohertz. So I'm going to start it at 500 kilohertz. Oops. Start it at 500 kilohertz. And then I'm going to stop it at 700 kilohertz. All right, that should get us a little closer to where we're looking at here. All right, so I'm going to set this for very close to 90 degrees. That's 82, 7, 8, 9, 90. Oh, there's 90 right there. Look at that. So the other thing that's interesting is the reactance is 50 ohms. The reason why I do this is because for the shunt method, the VNA is most accurate when the reactance is 50 ohms. So that's something I'm gonna maybe look into in a future video. I actually sent an email off to one of the engineers down in the States that works very closely with vector network analyzers, and he has published some formulas and methods on using VNAs accurately to measure component values. And I posed this question to him, and I asked him where is the most accurate point to measure using the shunt method, and he did a little bit of math and sent me back a spreadsheet, and it came out to be 0 plus J50 ohms for inductors and 0 minus J50 ohms for capacitors is the most accurate point on the Smith chart for measuring the nominal values of components. So this is why I do this. There's been some comments online. I know that You don't have to do that. You can measure it anywhere, and while true, you don't have to be right on 90 degrees. You can still get close to the value, but I choose to use that 90-degree mark because it keeps me far away from the self-resonant frequency, and I know that it's within that maximal accuracy point for this particular method. We're working with the method is what we're doing, so instead of against it. All right, so what we've got here at 90, we're measuring 14.8 microhenries for the inductor using this method here. So let's go ahead and attach the capacitor and see what it measures. Okay, so we're gonna set the capacitor in here exactly where the other one was. Here we go. And we're going to use the same method. We're going to now, instead of being up here because it's a capacitor, we should be looking at something down here. So now you can see where the marker is over here. I'm going to span out a little bit here. Let's see here. So our start frequency, I'm going to go back to just 10 kilohertz and then stop at 20 megahertz, and let's see if we can find that. Yeah, no, I don't see the self-resonant point at all here. No, it's not there. It might be higher in frequency, but anyway, let's see where we get to the 0 minus J50 point on the Smith chart is here, and that frequency is 3.4 megahertz. So I'm going to zoom in a little bit here and get a little bit closer. So 3.4. So I'm going to start at 3.3 megahertz and stop at 3.5 megahertz. There we go. And let's try to get minus 90 degrees here on our phase angle. There it is. And that happened at 3.432 megahertz. So I'm reading 928 picofarads value on that capacitor. And so the marked values are 15 microhenry and 1000 picofarads. But what I'm going to do is I'm going to test the measurement accuracy of the method and the VNA here that I've presented to you. We're going to build a parallel resonant circuit out of this inductor and capacitor, and we're going to make some measurements on that to verify that the behavior is as expected based on a calculation. So first I'm going to draw you a picture of what we're going to set up here. So what we've got here is the VNA. All right, so there's our nanoVNA. Here's port 1, here's port 2. So port 1 is going to come out like this, and we're going to insert the capacitor here. All right, and then we're going to come out here and we're going to insert our inductor. And of course our measured values was 928 picofarads and 14.8 microhenries. So now the question is, what is the expected frequency of resonance of this circuit? So of course we know the formula frequency will be equal to 1 over 2 pi times the square root of L times C. So we're going to go ahead and do the math on this and see what the answer is here. Okay, so I've gone ahead and brought out the rusty trusty Texas Instruments 89 calculator, and to spare you the boring difficulties of entering the formula into the calculator and spitting out a result, I've gone ahead and done this here off camera, and our expected frequency of resonance is going to be 1.358 megahertz. So let's go back to the nanoVNA and see what we get. So first off, we're going to need to reconfigure the components. So I'm going to take and reconnect the capacitor from the input to the output here, and I'm going to add the inductor. We'll insert that into the sockets there, and there. All right, now we should have a parallel resonant LC circuit. All right, so with regards to setting up the VNA for this measurement, what I've done is I've gone and selected trace 0 here, and I've adjusted it so that I'm reading the log mag of, 1 second here, channel S21. So what I want to do is I want to see where that dip is going to be in the signal level coming into port 2. So as this parallel resonant circuit goes into resonance, what happens is it actually creates a high impedance. It presents high impedance to this signal here, so that there's going to, at the resonant frequency, so that there's not going to be very much coming through to port 2. So what this log mag is showing, that dip there is where that is taking place. So I've also gone and adjusted my frequency span from 10 kilohertz to 10 megahertz to try to find where this spot is, where that frequency of resonance is. And then to locate the frequency of resonance, of course, I go to the 0 phase angle. So let's zoom in here a little bit more, and I see that this is 1.308. So we're going to go back and change our stimulus. So I'm going to start at 1 megahertz, and I'm going to stop at 1.4 megahertz and see if we can get a little bit more detail. All right, so let's see, what did I go to here? 1 megahertz, we are at 1.3, so let's go to 1.2 on the start. 1.2 megahertz here. There we go. All right, let's zoom in a little more, and we want to go to the 0 crossing point where the phase crosses over and the reactance crosses over from positive to negative, and we want the 0 point here where that transition event happens. That's resonance there, and the resonant frequency measured is equal to 1.344 megahertz. That's pretty darn close. So I'm thinking that these values as measured here are more accurate than the nominal values marked on the components. So again, I went ahead and did rework this formula using the nominal values on the calculator. And so if these were closer to the nominal marked values, we would be expecting, for nominal, a frequency of resonance of 1.299 megahertz as opposed to 1.358. And you can see that our measured using the nanoVNA is 1.344, so this measurement method is producing good results. Okay, so here's another question with regards to the accuracy. You can see 1.344 megahertz was the measured using the nanoVNA, and we were expecting 1.358. So just how far off is this? Well, to put this into perspective, what I did was I took and I replaced 14.8 microhenries with X in the my calculator here. So let's write this out here. So let's say 1.358 megahertz is a given, is equal to 1 over 2 pi times the square root of L times 928 picofarads. So on the TI calculator, I took and rearranged this formula and used X here, and I said solve for X to find out what value of inductance would give me the expected frequency. So let's go ahead and hit enter here. And there it is. So the expected inductance, L, would be equal to 14.8011 microhenries. So in order for us to get the measured frequency of resonance, we would have needed to have an inductor of 14.8011 microhenries. So when we made the measurement on this, we got 14.8. So just to put this into perspective, the nanoVNA can't even measure these values down here, as far as I've found so far. So as far as accuracy, this is bang on. And so this arriving at this frequency here in the actual measured circuit, it gives me a very high level of confidence that the actual measured values are in fact correct. So now that we know that this is working, the next step is to take the old BNC with Alligator leads on it, the test cable, hook that up, calibrate it, test these values, mark them down, and see what the difference in value measurements are between using this confirmed good test apparatus here, test lead set here. So we're going to go ahead and get that changed over. We're going to do the calibration on it, and I'm going to even show you how I do the calibration. We'll see what the difference in accuracy is, whether it really makes a difference. All right, so I've got the Alligator clip leads hooked up to the nanoVNA here. So before we go ahead and do the calibration, we need to adjust our stimulus back to the desired frequency range. So I'm going to start again at 10 kilohertz, and I'm going to stop at 20 megahertz. And then we're going to go back into the calibration screen. We're going to reset everything we did previously, and then I'm going to go to calibrate. Now, to do this, for the open, these clip leads are simply left open, and short, of course, is connected together. Wait for the screen to stabilize. There's our short, and then our load. This is a 50 ohm RF dummy load, and I'm just gonna hold this red Alligator clip to the center pin of the N connector, and we'll see that it's stabilized there now. Yep. Okay, and we're not doing the through, so we're just gonna hit done, and we'll save it in number 1. All right, so there's our open. There's short. And now we're going to measure the components and see if there is any difference. All right, so there's our 15 microhenry inductor. Now, of course, according to the method that I've presented, we go to the 12 o'clock position for an inductor, which should be close to 90 degrees phase angle here, and that's about 600 kilohertz. So we're going to have to zoom in a little bit here, stimulus. So let's go to 500 kilohertz and stop at 600 kilohertz, and see if we can get into that 90 degree point right on the button there. There's 90.00, reactance 50 ohms, 534 kilohertz. We are reading 14.9. So this is with the Alligator leads. We measured 14.9 microhenries on the inductor. Now the capacitor. See what we got here. It's at minus 17. So I'm going to zoom out again. So I'm going to go to, let's say, 10 kilohertz and stop at 10 megahertz and see where our 90 degree point is from negative 90 degrees. So we're going to be at the 6 o'clock position on the Smith chart. Right here. That's at 3.56 megahertz. So I'm going to go to 3.4 megahertz and stop at 3.6 megahertz. Dial it in a little bit. There's 90 degrees. And we are at 916 picofarads. so you can see the difference in the readings. They're pretty close, but there is a little difference. I guess it depends what it is you're trying to do. If you just have a handful of components and you have the Alligator leads and you just want to know if this is what this is approximately, you can plug them into the Alligator leads. It's going to tell you it's approximately 15 microhenries. You look at this value here and you say 15, yeah, it looks like that's a good inductor, so we can put that into the good bin again. As well, for capacitors, it's going to give you a value that's pretty close, but if you're trying to build a circuit with it, I'm probably going to go with this one because I think it gives more accurate and repeatable results. So that's the conclusion for today, and thank you for watching. This is Victor Echo 6 Whiskey Golf Mike. Until next time, we'll see you later. 7-3.